Hi, everyone. Go over linear regression. We're going to go over some of the assumptions of linear regression. As I've listed out here, we're going to go over how to show that these assumptions are violated, how to show that these are not violated. We'll also go touch more into the different evaluation metrics when we're evaluating models. We'll go into AIC, BIC, what that means. We'll go into how to actually select these different models, forward selection, backward selection, the difference between those two. We'll go into regularization methods, ridge regression, lasso regression, cross-validation. And then we'll sort of touch a bit, not entirely a bit on generalize the linear models. We'll end. And in the next video, take a deeper dive into why we need generalized linear models and the entire math and interpretation of the R output and things like that. So let's start with linear regression. So in linear regression, we are trying to model the output variable y with this linear form using a bunch of predictors. And we also have some of these different assumptions that we want to make sure that we know. So the first one is, let's first get into this concept of an error term. So we know that whenever we have a linear regression model, we know that's not going to perfectly capture the relationship between x and y. So we know that in real life scenarios, we know that there could be this linear relationship. We know that there could be, in general, a linear relationship between these two variables, but we know that's not perfectly the case. It's not going to be the case that two variables are exactly perfectly linearly related in really any situation. Yeah, they may be correlated or we may see some relationship, but it's very unlikely that they're perfectly exactly I have this linear regression relationship. And so this error term really is the unexplained variation in the dependent variable that the model doesn't account for. So one of the analogies that I like to use to explain this is if you have a photographer and he has this ideal photograph that he wants to take when all of the settings, when all of the lighting, when the subject has minimal movement, when he's not moving, when everything is perfect, that's the ideal photograph that he wants to take, that he or she wants to take. But in reality, that actually might not be the case. You might have some sudden subject movements or you might have sudden lightning changes. That actual photograph is probably going to be really a bit different than what the ideal photograph you had in mind with all the perfect settings in place. So that difference is what we consider the error term is we know that our model is not going to perfectly capture this relationship. And so a lot of that unexplained variation, that difference is captured by this error term. And it is a random variable. So it will take on many different values. In expectation, one of the assumptions is that we expect this error term to be zero. So in the perfect world, ideal world, we expect that the ideal photograph is the one that we actually take itself. So that's one of the assumptions. We assume that the variance of these error terms is constant. It follows this constant sigma squared. And then we'll show how to go about knowing when this assumption is actually violated. We know that all of these errors, and one of the assumptions is that they're independent. So the difference between one perfect photograph and the actual photograph shouldn't affect the difference between another photograph, the ideal photograph for another subject and the actual photograph. So we know that these errors are independent. They don't influence one another. And we also know that they're normally distributed. So we'll go more to how to test that if they're not normally distributed. And then the fifth assumption is that these predictors that we have in our model, they're not a linear combination of the other predictors. So if they were a linear combination, then we're not really adding anything to our model. We're just saying the same thing, just in a different way. So if we have a predictor and that's like exactly 2 times x1 plus 3 times x2, that's a linear combination. We're not adding anything to the model. And so yeah, we talked about error terms and we talked about that these represent the difference between what our actual outputs look like, what the actual y variable is, and what our model actually predicts. And it really accounts for the unexplained variation that our model doesn't account for. These factors that are not directly captured by these different independent variables. Because there's going to be like some noise, there's going to be just other things that we haven't really considered that doesn't and that's why it doesn't perfectly follow this linear relationship that we have modeled it with. So let's we also have yeah, that's called collinear. Number 5, that's called collinearity. So when we have different dependent predictors, what does that actually mean? Um, And then, so another issue is like we may have outliers and we may want to detect high dimensions. So in high dimensionality, as the number of predictors increases, we're going to need more observations to make sure that our model is going to be adequately fit to the data. And then, okay, so now let's go into the different violations and how we can see that each of these assumptions is being violated. So the first one is this expectation of the errors being 0. So this means that the predicted value is equivalent to the actual value. So how can we see this? How can we violate? How can we see that a violation in this assumption has been achieved? So the first thing, or the first assumption is that, or the first way to detect this is to see whenever we plot our fitted versus residuals plot, we see non-zero averages. So if we average these different points along this plot, our residuals on the y-axis are predicted fitted values on the x-axis, and we see that we have non-zero averages. So in this case, you can see between like this middle section that there's actually a large number of negative residuals, and so we see that the average is probably negative in that section. So we see that there's not a zero average. So there's a non-zero average there. So whenever we see that, even if we see that in one section of the plot, we have evidence to show that the expectation of our expected value of our errors is probably not 0. Next, same plot where we have the residuals on the y-axis and the fitted values or the predicted values on the x-axis. And if we see this non-constant, inconsistent spread of the residuals, then we have evidence for heteroscedasticity, where our errors actually don't represent or have a non-constant variance. And so here in this case, we can see that with lower fitted values, all of these points are clumped together, whereas when we have higher fitted values, our points are more spread out. So we see the inconsistent spread of these residuals throughout the plot. We could also measure this through scale location plots, where on the x-axis we have the square root of the standard residuals, y-axis represents the fitted values, and we can see sort of in the same way, we can look at the spread of these data points, and if they have an inconsistent spread, then we have evidence for heteroscedasticity. And then we can also check for dependent when the errors are actually not independent, if they follow this certain pattern. So they don't need to follow a U-shape. If you find that these errors form some sort of general pattern, then we know that that pattern could actually be described by another predictor. So it's possible that there could be another predictor that we add to the model, and so the errors don't really follow a general trend or a general form. And that's really why they're doing that. There's probably a predictor that's missing that's going to explain a lot of that trend and a lot of the reason why the residuals are behaving in that way. So that's the way to detect if the errors are dependent, which would be a violation of the third assumption. And then we have QQ plots. These describe if this is how we figure out if the errors are actually normal or not. So this compares the distribution of the residuals to the theoretical distribution, which is normal. So that's what they should be. And if we see if these points follow along this line, which represents the normal distribution, and then we have reason to believe that, okay, this assumption is probably met. And even if if they're off, if they don't follow the trend of the line, then we have reason to believe that this assumption is violated and they're probably not normally distributed. The errors are not non-normal. And then the standardized residuals versus leverage plot showcases influential points. So these are different from outliers. These influential points are actually, they only have to do with X values, which X value has the highest influence on on our model. So Cook's distance, we won't get too much into what influential point versus outlier actually mean, but this plot, standardized residuals versus leverage plot, they can show these influential points. Perfect collinearity. So we mentioned collinearity, and that's about the linear combination of our predictors. So if we have two predictors, if we have predictors that are correlated, highly correlated with one another, that's what we call collinearity. And perfect collinearity is often caused by when we have many different models or predictors in our model. So if we have a lot of predictors, that increases the chance that many of these predictors are going to be highly correlated with one another, increasing collinearity. Okay, so let's go into F tests. So as we talked about T tests in the previous version, in the previous video about exam PA and ML, we talked about how T tests only test the impact of a single predictor. So if we have this one predictor and our T test, or our p value is less than 0.5, then there's evidence to suggest that this single predictor actually is significant in predicting the outcome variable in our model. But this doesn't allow us to test multiple different predictors at a time. It's possible that a single predictor isn't influential, doesn't have significant value in the model, but when it's put together with other different predictors, then it has significant influence in the model. So F tests actually allow us to do this. So they assess multiple predictors together, unlike T tests. So our null hypothesis, or when we do a simple model fit in R, we can see at the last line of the summary, we can see the F test and F statistic, and we can see the p-value for that. And so if our p-value is less than 5, we see that our model that we have is a significant improvement over the null model. So this means that at least one of the predictors that we have in our pool of predictors is significant compared to the null hypothesis, which is that the model is not a significant improvement over the null model. The null model would be a fine model for this data set. And so now what do we do when we want to compare multiple of these different models, where we're not comparing to like a null model or the intercept only model? So if we have model 1 and model 2, we can use ANOVA output to determine the significant, if model 2 is a significant improvement over model 1. So we can see the null and the alternate hypothesis, and we can see that if our p-value is less than 0.5, we can see that model 2 would be a significant improvement over model 1, which means that at least one of the additional predictors in model 2 is not 0. So at least one of the predictors, additional predictors that model 2 has, is contributing to determining the output of the dependent variable. So we also have the formula for the standard deviation, or for the sigma over here. So it'd be the standard deviation of the error. So that's how we can get that, an estimate for that. We also have model evaluation metrics. So after we federate model, how can we evaluate the model? How can we compare two different models? Well, we have a couple of two different metrics. One is AIC and one is BIC. So we have the formulas for here. You can see both of them include the sum of squared errors. So sum of squared errors, this is the sum of the squared between the actuals minus the predicted. So y minus y hat, square that, the sum of those, and then the sum of those. Take the sum of that. That's SSE. And then we have 2p, where p is the number of predictors. Now, let's see what we want to test here. So one thing to know, probably the most important thing to know between AIC and BIC is that BIC favors models with fewer predictors more than AIC does. So BIC generally is going to favor models that have fewer predictors, because it penalizes the term that calculates the predictors, that does the calculation with the predictors, more than AIC does. So we can see when n is greater than or equal to 8, when the number of observations is greater than or equal to 8, then our ln of n is going to be greater than 2, which is AIC. So AIC is 2p. This is ln of n times p. That term for BIC is going to be greater than AIC when n is greater than or equal to 8. So that's the main thing, that BIC is going to generally favor models with fewer predictors. And then let's go into model selection. So how can we select different these models? So we have 3 different approaches: forward, backward, and best subset. The 2 greedy approaches are forward and backward. Here we start with a model. So in the forward selection approach, we start with the null model. Backward selection, we start with the full model. And we iteratively determine which predictor to add that's going to optimize the AIC or BIC value, or in this case, that's going to yield in the lowest AIC or BIC. And then that's our new current model. Then we continue to add predictors, see which one's the best one that leads to the lowest AIC, BIC value. And if we get to a point where adding none of the other predictors is going to cause us to have a lower AIC or BIC value than we already have, then that's where we stop. And so that's how forward and backward selection are ultimately done. And forward selection performs very well in high dimensional settings. So if we have a high dimensional data set, we would want to use forward selection. Best subset selection, it compares all different possible models from the available predictors. So unlike forward and backward selection, which is a greedy approach in which we're iteratively looking at the next best model to pick based on the pool of predictors that we have, best subset selection takes into account all possible models. And so what we want to know is that forward selection with BIC, it favors fewer models in the chosen model, where backward selection with AIC, it favors more predictors. So yeah, did I say that correct? So forward selection with BIC favors fewer predictors in the chosen model. So if you're looking for higher interpretability, if you want only the best predictors that can explain the dependent variable really well, that's forward selection. You want to use forward selection with BIC. If you're looking for more predictors, if you're looking for a more flexible model that can really capture the trends in your data, the nuances, the specifics in your data, and if your focus is on accuracy, then you want to use backward selection with AIC. Then let's get into the concept of regularization or shrinkage methods. The entire idea of this is we want to reduce the variance of our model. We want to increase bias. So we want to increase the underfitting that we do. And the reason that we want to do this is so we can generalize to more unseen data, right? We don't want to overfit our data too much. We don't want to really capture the trends in the data. We want to make sure that this model performs well to new unseen data points. And so we have two different approaches for this, or three technically. We have lasso, ridge, and then we also have elastic net, which is a sort of hybrid between these two. So ridge regression is very useful in high dimension. So in general, the idea of the regularization is we're minimizing the SSE plus another term. And now for ridge, that other term is lambda plus the sum of the coefficients squared. So lambda, you can think of this as the regularization, or it is the regularization parameter. So as lambda increases, our flexibility is going to decrease. So this means that we're going to be less able to capture a lot of the specific trends in the model, and we're going to be more ready, and we're going to have a high, we're going to have a high bias. It's going to underfit our data, but that's going to allow us to do well with unseen data points. And another thing about ridge is that it will not allow us to remove predictors, because beta can approach zero, the coefficients can approach zero, but they won't be exactly zero. In the case of lasso, when we're minimizing lambda times the sum of the absolute value of the coefficients, then as our lambda increases, our betas can actually approach zero. And so this is actually a feature selection algorithm as well, where this actually allows for more easier interpretation, because it's possible that our betas can be zero, where we can remove predictors. And then cross-validation is essential when we're selecting the optimal lambda to use. It's also essential just measuring overall performance of the model. So we have k-fold cross-validation that's commonly used, and in which we use k-1 folds for the testing of the data, and then we use the k fold for the training of the data. We use k-1 for the training, and then we use the k fold for testing. And we can do this for all k folds. And the advantage of doing this is that we're able to train our model, and we're able to test it on different subsets of our data. And so that's going to give us a better measure of the accuracy and the performance of our model. And elastic net regression is a subset of ridge and lasso, where we have a lambda, where we have specific weights of how much weight we want to give to the lasso and edge, lasso and ridge additional parameters that we have. So you can see that here. And this is like sort of the mixing coefficient, like how much do we want to give the weight to each. And as I mentioned, or as I think I mentioned this before, but shrinkage methods are very good for high dimensional data. And if we want to reduce the variance, we want to reduce a lot of the overfitting. And the reason we want to do this is, again, we can generalize our model so we can predict well on unseen data points. Now we have generalized linear models. So now we talked about linear regression, the entire idea that our errors are normally distributed, or y. Our dependent variable, we're assuming that it's normally distributed, but now what do we do when that's not the case? Our dependent variable could follow a Poisson distribution, or a Bernoulli distribution, or a gamma distribution. What do we do when that distribution is not normal? for being a part. So that's in a Y distribution comes from a linear how we calculate the expected value of those, the variance of those from those different parameters here. We have shown here that Poisson is from the linear exponential family by showing what these parameters would equal when we write it in this format. So that's, again, so to recap, we covered linear regression assumptions. We went through the different assumptions, errors being normal, the expectation of the errors being normal, having constant variance, them being independent, they're normally distributed. We talked about collinearity. We talked about the predictors, any predictor not being a linear combination of the other predictors. We talked about also residuals. Another way to know that is it's AP statistics. So if you're taking AP statistics, you can think of it as actuals minus predicted. We talked about errors, what those sort of represent. There are a lot of the variation, unexplained variation that's not captured by the other different independent, other different variables in our model. And we sort of gave the analogy of photographer, an ideal photograph versus the actual photograph that he takes, with a lot of the changes that's not accounted for, that's not expected. And we talked about how to go about seeing if these violations are met, seeing if the assumptions are met or if they're being violated. So we went through the fitted versus residual plot, how we can test for expectation of the errors not being zero. We can test for the variance of the errors not being constant. We can test for dependent errors. We can test for the normality of the errors. We can also see if they're influential points. Talk a little bit about F-tests and how they allow us to compare predictors together and how they influence the model. We talked about the different evaluation metrics, AIC, BIC, how they're one of the main things is that BIC favors models with more predictors, and we went through the formulas for each. Right, we know that BIC it severely penalizes the term that accounts for the number of predictors in the model. And we talked about the different ways we can select our model, to different ways we can build our model, forward, backward, best selection. Talked about regularization, how that's reduces the variance in our data set, increases the bias. Talked about cross-validation, and then we introduced the idea of generalized linear models. We'll move into generalized linear models and some of the other topics in PA in the next video, but thank you very much, and I hope to see, and I'll see you in the next video. Thanks.